Hello everyone, welcome to my channel. This is the start of a series of lessons I'm going to have on Euclidean geometry, and I'm starting with psychogeometry. Now in this video I have two theorems that I would like to prove and one application for each theorem. So theorem number one, I have a name and statement. You'll understand why I have a name when I start looking at applications of these theorems. So the name of theorem number one is a straight line from center to midpoint of chord in that short form. Statement says a straight line from the center of a circle to the midpoint of a chord is perpendicular to the chord. So here's the construction. So basically we're required to prove that OM is perpendicular to AB, given that O is the center of the circle and M is the midpoint of the chord AB. So how do we go about it? Well, here is the proof. So I'm going to use the same diagram, just go straight to proof. Obviously, as you can see, we're going to use congruency of these two triangles. So we have side, and the common side OM. So because it's a theorem, we have to start with given. So theorem number one. So maybe I should capture the circle first. And I have a chord AB. And I have a center somewhere here. We have a straight line from center to midpoint of chord. So let's call this M. Of course, that's what we have in the construction up here, as you can see. Now, we need construction, so we draw radii AO and BO. So that's our O. And because these are radii, they must be equal in length. So we start with given, because this is a theorem. What are we given? Well, we're given circle AB. Remember, we named the circle around it. Circle AB with center O. And M is the midpoint of AB. That's what we're given. So we're given AB with center O and M being the midpoint of AB. What are we to do next is to say, to prove that, or required to prove. I like to say to prove that, but some people say required to prove, RTP. What are we required to prove? Well, we're required to prove that OM is perpendicular to AB. OM is perpendicular to AB. Construction, do we need it? Yes, as you can see in the diagram. Construction. We need our construction, and our construction is draw radii AO and BO. Right, next we go to proof. And we're going to say in triangles AMO and BMO. In triangles AMO and BMO. What do we know? Well, we mention one item in here equal to another item there. Or one aspect here equal to one aspect there. So we know AO is equal to BO. And these are radii. You can say construction and radii. So let me start with radii. And then I'm going to say construction. Right. What else do we know? Well, we know that AM is equal to BM. Why is that the case? Well, we're given. It's given up here. M is the midpoint of AB. That means AM equals BM. What else do we know? Well, you can see that OM is common. Some people say OM is equal to OM. It's the same thing. So OM is common. And now we have three items mentioned sufficient for us to conclude congruency. So therefore, triangle AMO congruent to BMO. So triangle AMO is congruent to triangle BMO. Why are these triangles congruent? Because of side, the common side, and the given side AM being equal to BM. So side, side, side. Next, we now can say hence angle AMO is equal to angle BMO is equal to angle BMO. Why are these angles equal? Well, they are corresponding angles of congruent triangles. Corresponding angles of congruent triangles are equal. But you can agree with me, but angle AMO plus angle BMO, AMO, BMO, these two angles must add up to 180 degrees. Why? Because they are adjacent angles on a straight line. That means if two angles are equal and the two angles add up to 180, each one must be 90. So therefore, we are basically saying AMO, this angle equals angle BMO, and the answer must be 180 divided by 2. And what is that? 90 degrees. Now, if this angle is 90, AMO is equal to 90 and BMO also 90, it tells us that OM is actually perpendicular to AB. The conclusion is therefore OM is perpendicular to AB. And that's what we're required to prove up here, as you can see. So you can simply add this QED like we like to do when we're proving geometry theorems. I basically is saying this is what we were required to prove, as required to demonstrate or to prove. Right, so theorem number 1 done. Let's look at theorem number 2. I want to talk about theorem number 2, and then I'm going to come with applications of the two theorems. Right, theorem number 1 completed. Let's move to theorem number 2. Theorem number 2 is this one. This is theorem number 2. We're on page 3 now. Theorem number 2, the name perpendicular from center to chord. Statement, the perpendicular from the center of the circle to the chord bisects the chord. Sort of the converse of theorem number 1, the opposite of theorem number 1. So how do we prove this? Well, again, we are told, remember, we're given that ON is perpendicular to AB this time. Of course, we are going to need construction, AO and BO joining or drawing those radii. Again, congruency comes in handy because we're going to say that these two sides are equal, radii, construction. This side here, ON, is a common side, and then we have angle ANO being equal to angle BNO, and these are 90 each because we've been told here that ON is perpendicular to AB, and that should prove that AN is equal to BN, because then they are corresponding sides of congruent triangles. So let's write down the proof. So the proof is set out as follows. For theorem number 2, like I did in theorem number 1, I'm gonna redraw the circle briefly like that, and we have our chord AB, and we have a straight line from center there, which is obviously perpendicular. This time we're told it's perpendicular to the chord like that, and let's call this point N, as I have indicated in the construction up here. Let me move this one down. As I've indicated in this construction here, we're going to call that down this point N, that point, and our center is O. Again, construction like we said, like that, and we know that these are radii, so that equals that. That line equals that line. So like I said in the theorem number 1, we have to start with given, because this is a theorem. What are we given? Well, we're given circle AB. Circle AB. What else do we know? With center O. In which ON is perpendicular to AB and we know, and N is on AB. So ON is perpendicular to AB and N is actually on AB. To prove that, or required to prove that, or required to prove, some people say required to prove. What are we required to prove? Well, we're required to prove that AN this time equals BN. This is what we're required to prove. Do we need construction? Yes. Not all theorems need construction, but these two need construction. First one and this second one. Construction, we're required to draw radii AO and BO. And then we go straight to proof. What are we saying? Again, in triangles, ANO and BNO, ANO and BNO, what do we know? Well, we know that AO is equal to BO. These are radii. And of course, it's because of construction. What else do we know? We know that ON is common. Is found in both triangles. That's what we mean when we say ON is common. You can see that ON is part of triangle ANO, and ON is also part of triangle BNO. So ON is common. Some people say ON equals ON. It's the same thing. What else do we know? We also know that ANO, angle ANO, is equal to angle BNO. Why are these angles equal? We're told this is equals 90, and it's because we're given that information. It's given up here. ON is perpendicular to AB. Now, some people like to number this one as 1 and 2, and then they say N1 equals N2. It's the same thing. Right. So, conclusion, therefore, triangle ANO is congruent to triangle BNO. Be careful how you name these congruent triangles. Notice that here I said ANO. A corresponds to B, and N, obviously the two angles are equal there, and obviously O in this triangle corresponds to O in that triangle. So we have to name congruent triangles by following equal angles like that. So what is our condition in this case? Well, we have a right angle, the hypotenuse, and the common side. So it's RHS, right angle, hypotenuse, and the common side S. What is our conclusion? Well, our conclusion is, hence, first two, that's AN, will be equal to first 2, BN. Why are we saying that? Because these are corresponding sides of congruent triangles. And that's the end of the proof. Remember, we are required to prove that AN equals BN, and that's what we got. So, like they say, called erat demonstrandum. Basically saying this is what we're required to prove, and we've just proved it or demonstrated it. All right, now I want to look at applications of the two theorems. Applications of the two theorems. Let's look at the first application of theorem 1, and I'm going to need theorem 1 and 2 close by for the sake of the name. Remember, I told you that we're going to use the name as a reason in problem solving. So theorems, remember theorem 1, the name, a straight line from center to midpoint of chord. Theorem 2, the name, perpendicular from center to chord. Let's see how we apply these theorems in problem solving. So we have the first problem here. Here it is. First problem. We're on page 5 now. The first problem is we're required to calculate radius of the circle with reasons. So question 1. In circle ABC, O is the center, right? And we're told that AC is equal to 24 centimeters. AC is 24 centimeters. BD equals 8 centimeters, BD equals 8 centimeters, and D is the midpoint. All right. So that means AD equals CD. What else are we told? We are also told that ODB is a straight line. ODB is a straight line. And because that is the center, you can see that ODB is actually a radius of the circle. Now, we're required to calculate radius of the circle. In other words, OA or AO, CO, BO. We're required to work out that distance. Now, how do we approach this? Well, like we did when we're proving theorems, we need construction there. So this is applications. Question 1. Let's say application of theorem 1. Now notice that I'm calling this theorem 1. Someone else may call it theorem number 2. That's why it's important to know the name and the statement. Right. So let me capture the question. I'm going to draw the circle. There you go. And we are told that we have that line there. And this line is AC, not drawn to scale. Just what we need to be able to solve the problem. So this is BD. We are told that that length is 8 centimeters. And that's our O center. We need that construction there. We are told that this length AD equals CD. Right now, first of all, we quickly understand or mark that AO is actually our radius. Let's use small letter r there for radius. You'll agree with me that I can therefore also say that OD plus BD is equal to r, because that's radius also. So what is BD? Well, BD is 8. So OD plus 8 equals R. Let's work out OD. OD equals R. OD equals R minus 8. Keep that one there. Now, what else do we know? Well, we know that a straight line from center to midpoint of chord is perpendicular to chord. I told you that. This is theorem number 1 application. So we're now going to say, let me draw a line here. We're also going to say OD is perpendicular to AC. Reason for that is a straight line from center to midpoint of chord. That's the reason for that statement. Check this out. Theorem number 1. There it is. A straight line from center to midpoint of chord. A straight line from center to midpoint of chord. That's the reason why we're saying this angle should be 90 degrees. Right. Now that we have that settled, we can also say, remember, we have been told in this question here, we have been told that AC is 24 centimeters. AC is 24 centimeters. So from here to there it's 24. But we know that D is the midpoint of AC. So we can say therefore that AD, which is also equal to CD, it must be half of what? Of AC. The reason for that is D is midpoint. Of AC. So what is this? This is half. Remember, AC has been given as 24 centimeters. There it is. So 24. And that should be 12 centimeters. 12 centimeters. Right. So now I can pull out this triangle there. Pull out that triangle. It's going to look like this. That's how it's going to look like. This is my D. And that's my O. And that's my A. This is R. This distance here, we calculated, as you can see, it's R minus 8. That distance AD, as you can see here, AD is 12 centimeters. I'm going to put 12 there. Now we have to apply Pythagoras theorem in this triangle here. So we are now going to say, AO squared is going to be equal to AD squared plus OD squared. Why is this the case? Because of Pythagoras theorem. Now let's put in what we know. This is r squared equals AD is 12. We square that plus, and OD is actually r minus 8. We square that. This is going to be r squared, and that will be 144. Expanding this one here, it will be r squared minus 16r plus 64. Now you can see the r squared cancels, and add minus 16r on both sides. You're going to get 16r is actually equal to 144 plus 64 is 208. And solving for r here, basically we're saying that this implies that r will be equal to 208 over 16. And make sure you agree with me that this is actually 13. So our value of r is 13 centimeters. Worked out with reasons. Remember, one of the reasons, a straight line from center to midpoint of chord, that one has a mark on its own. And of course, don't forget to say that this is true because of Pythagoras theorem, which basically says in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So this is how we go about it. Now let's look at application of theorem number 2. Application of theorem number 2. I'm moving at a pace that is maybe considered slow pace, but I know that this is what is required for Euclidean geometry. Let's look at application of theorem number 2. Basically, it says that in circle ABC, O is the center of the circle. AC equals BD equals 16 millimeters. So O is the center. AC equals BD equals 16 millimeters. We're required to determine radius of a circle. Again here, with reasons. But we are also told that BOD is perpendicular to AC. Now, perpendicular from center to chord bisects the chord. That's theorem number 2, and that's the application we're going to. That's the theorem we're going to use in this one. So how do we go about it? Well, as we did in question number 1, applications number 1. Let's capture this question here, question number 2, and basically its application of theorem 2. The first one was application of theorem 1. I think I have somewhere here. We'll check it up. Yeah, I'm going to check it, but this is application of theorem number 2. So what do we have as a question? Let me draw the circle, right? And we have a chord like this, and we have a straight line from top there coming straight here, passing through the center O, and we're told this is D and that angle is 90. And if that angle is 90 and this is the chord, that angle should also be 90. This is our A and that's our C, and we are going to have to, okay, this is B and our construction is from the center like that. Let's call this R again, radius. Now what do we know? Well, what we know is, first we're going to say OD is perpendicular to AC. This has been given. We can say, therefore, AD is equal to CD. Reason for that is perpendicular from center to chord. Check theorem number 2. The name of theorem number 2. I'm gonna just get it now. Here it is. Perpendicular from center to chord. The name is what you use as a reason for that statement there, that AD is equal to CD. And that is true because OD is perpendicular to AC. That's given in the question. Right. Now, so that is sorted. Now, look at this. So we're basically saying this part equals that part. Now, what else what else do we know? We are also told that OD is equal to AC, and that is equal to, here it is, 16 millimeters. So we can actually say that OD plus BO. So first check that, make sure you can see that AO is actually equal to BO, and that's also equal to R. Remember, O is the center of the circle. So basically we are saying, maybe let me just work on AC first. So we are now going to say, therefore, AD must be equal to half of AC. If the reason for that is because D is a midpoint, as you can see now, or at least you can say that AC is bisected by the straight line from center O, which is perpendicular to AC, according to theorem number 2. So this is going to be, so what reason would you give for this, for saying that AD is equal to half of AC? Well, you say AC is bisected, or you can say D is midpoint of AC. So AC is bisected by OD, which is perpendicular to, AC. Right, just extending there, just for clarity's sake, but basically you understand what I'm trying to say. So this is going to be equal to half of, what is AC? Well, AC has been given as 16 millimeters up here. So this is going to be 16, and what do we have? 8 millimeters. Right. Now, we are also told that AC equals BD. Here it is. AC equals BD equals 16. So AC equals BD. So we are now saying, check this out. We're saying BO plus OD is equal to BD. BO is R plus OD, which we don't know, is equal to, what is BD? Well, we're told BD is 16. So clearly from here you can see that OD is actually equal to 16 minus R. Now, pulling out this triangle here, like we did in example in problem 1, we're going to get a triangle that looks like this. That length there is actually 8 millimeters. This distance here from O to D is actually 16 minus R, and that is our R. Applying Pythagoras theorem, this is A, remember, we're going to say AO squared is equal to AD squared plus OD squared. Why? Because of Pythagoras theorem. Pythagoras theorem. THM, just for short. All right. Now, let's put in what we know. So this is R squared is equal to, what is AD? Well, 8 squared plus OD. It's 16 minus R. And we have to square this. So this is R squared is equal to 64 plus 16 squared, 256, minus this times that, times 2, it will be 32R plus R squared. Expanding, convince yourself that the expansion of this one is this expression here. Again, you can see that the if you subtract R squared from both sides, you're going to have 0 is equal to, these two, adding them up is actually 320 minus 32R. Bring 32R to the left, or add 32R on both sides, you're going to get 32R equals 320. Dividing by 32 both sides, you'll agree with me that R is going to be 320 over 32, and the answer is 10 millimeters. Remember the unit we have? 10 millimeters. So that would be the radius of this circle. With reasons, that's how you go about it. All right, I'm going to stop here in this video. Remember, I have covered 2 theorems with 2 applications. In my next lesson, I'm going to be looking at theorem number 3 theorem number 4, and so on, and I'm moving on until I complete Euclidean geometry. So, and I hope that you thoroughly enjoyed these two and applications as well. All right, if you're new to the channel, please don't forget to subscribe and give us a thumbs up. Share these videos with friends. It will help us to grow the channel and develop and present as many videos as possible. All right, see you next time.